start. Hello. And now I'm going to hide the floating meeting controls. Hello for the third time. Today we are doing PWN, or binary exploitation. So this is the first meeting on PWN. If this is something you're interested in and want to learn more about it, we're going to be covering more about it on Sunday with Kevin. So awesome. Let's get started. There we go. So there's the meeting flag. It is SIGPwny. That's like 24 A's, I think. So like
should be 24.
I think it's 24. So and then the relevant XKCD is the heartbleed bug, which is a form of length manipulation or kind of like a buffer overflow. It was the most relevant XKCD we could find to today's meeting. So, all right, and then quick announcements. So to a few of us, specifically 8 of us, are going to Purdue tomorrow for a Purdue trip. So that's Sandia National Labs. Thank you, Sandia. Is sponsoring 8 people from SIGPwny to go to Purdue for just like a seminar and tournament. So that'll be really, really fun. Then we've got the fall recruitment event that is next Saturday. So again, that is Saturday the 23rd. It's from 12 to 6 p.m. in Siebel 1404. And if you're interested, there will be pizza. There will be probably people to talk to from industry. We're still working on that. But there will be prizes too. There will be pizza and prizes. So if you're going to show up to the pizza and prizes. And then Halloween party on October 31st, which is Halloween. We are going to do a Halloween party in replacement of the seminar. So that will be fun. It'll give everyone a chance to just have a nice quiet break. Details of that will be probably coming next week. All right.
Cool. So let's get started with memory. When you load up a program, the layout of the memory space of that program sort of looks like this. Starting at the bottom, which is lower addresses, 0. We have the program data itself, which is broken into the text, data, and BSS segments. For the simplicity of this meeting, I'm not going to go into too much detail on those segments, but just know that that is the program data itself.
Did we skip a slide?
What?
I feel like we skipped the table summary slide.
Oh, we didn't make one.
I got it. Okay, what are we doing today? So what we're doing today is called binary exploitation. Before we go into memory, we're going to talk about what that actually means. So binary exploitation is the actual act of attacking programs when they are running, or like you have some amount of the program and then you run it and then you attack it. So a big part of that is control flow hijacking, which is what the big thing that we're going to cover today. And then the other big thing that we're going to cover today is memory and how that works at a lower level, just the basic understanding of that, and then how we can attack that. Does anyone have any questions about that before we get going? Anyone? All right, awesome. Now this makes more sense.
Yeah, now this makes more sense. So anyway, you have the program itself sitting at the bottom of memory at lower addresses. And then after that, you have the heap. I'll explain more what the heap is in the next slide, but for now, just know that as it expands, it grows towards higher addresses in memory. And then sitting at the top of memory is the stack, which grows towards lower addresses in memory.
There we go. So this is the more detailed.
Yeah, so this is a little more detail on what each of the sections are. As I said earlier, I'm not going to go too much into the 3 sections that make up the program itself. But the heap is dynamically allocated memory. So think of like when you use the new keyword in C++ or Java, when you allocate a new object, or in C when you use malloc. That memory goes into the heap section of memory. And then the stack contains the call stack, which is like the program arguments and local variables.
Got it.
So let's talk about smashing the stack. So to go into more depth on the stack, sitting at the top of the stack are local variables. And then past that is the RVP, which stands for base pointer. For the simplicity of this meeting, we're not going to talk about what the base pointer is, but it's important to remember that it is there whenever you're overriding things on the stack. After that is the return address, which we'll get into more later. And then after that is the arguments to the function that you are calling in. And then while that arrow in the diagram is going up, keep in mind that that's actually growing towards lower addresses in memory.
It's weird.
It's weird, it's flipped, it's not really intuitive, but it's something to keep in mind. So then an example, if you're calling a function method 1 with the arguments A, B, and C, those arguments would be stored on the stack in that order.
Yep.
All right, so let's talk about a simple buffer overflow. So on the top left here, there's a very simple C function called vulnerable. It calls puts, say something, and all puts does is just print that into the console. Then after that, it allocates a stack variable called stack var1, which is an array of 4 characters, which is 4 bytes. It then allocates a second stack variable called stack var2, which is also 4 bytes. Then it calls gets on stack var2. And what gets does is it takes whatever input the user puts on the console and then stores it into that given variable. And then the last thing this program does is it calls puts, which prints out stack var1. So an important thing to see here is that explicitly from the program itself, nothing is ever put into stack var1. It's just defined and then it's printed out later. The only thing where anything is ever stored is that gets call. So if you look to your right here, you'll see the layout of the stack. You'll see at the top of it is stack var2, 4 bytes, and then right after that is stack var1, which is also 4 bytes. And then, so in the bottom left here is an example of what the console would look like if you were to run this program. Notice the say something that is there from puts. And then if you, the user, inputted 4 A's and 3 B's, what would happen? So we know that it'll take that input and put it in stack var2. But stack var2 is only 4 bytes long, and your input is 7. So where do the B's go? And as you can see on the right, previously where stack var2 was in the stack in the blue, you have those 4 bytes, which are the 4 A's. But then after that, those 3 B's get stored in the stack var1, which you, as the programmer, never intentioned for anything to ever be stored in the stack var1. But because of the nature of how the stack works, that's where that extra data went. And so lastly, the last thing the program does is it prints out stack var1, it prints out those 3 B's.
So it's really important to note that this works because stack var gets is a well-known vulnerable function. And because it's a well-known vulnerable function, because gets is a well-known vulnerable function, it's exploitable. And it is exploitable because it doesn't do length checking. So the assumption right here is that, oh, I have stack var2. There's somewhere in this program that dictates that stack var2 is only 4 bytes. But in reality, that's not anywhere. What's actually gets is receiving is an address. It's not receiving a size. It's not receiving really anything. It's just receiving, hey, take user input and put it at this address. And the fact that it just assumes like, oh, they're only going to do 4 bytes is how it's vulnerable, because you can do more. Does anyone have any questions? No? All right. Is everyone kind of getting what's going on with like a buffer overflow so far? Awesome, because we're going to do something.
So I guess to explain the term, since we didn't really say that.
Yeah, true.
In these term buffer overflow, buffer would be stack var2. It's a buffer of 4 bytes. And then the overflow is what happens when you put more data into the buffer than is supposed to be there. That's the overflow part of the term.
Yeah. So you can do this with pwn tools. So I believe this is stack 0. You can connect to it with netcat. So I'm going to explain this line for line about how we're going to do this. So pwn tools, again, is a really great library. I think we covered it in the important tools for security meeting, and we'll make sure to link that in like the club general or something like that. If someone wants to go do that, that would be awesome. So if you want to learn how to get pwn tools set up, you can probably just pip install it.
Yeah, it's at the bottom there, how you can install it.
Oh, is it? Okay, cool. Python 3, TACM, pip install pwn tools. So that'll install pwn tools, and then first thing you do, you import pwn tools. Then you can create a remote connection with something called netcat, which we also covered in that meeting. It's basically just a way to do a raw TCP connection to a server. And then you're going to remote in using Netcat, and you're going to print the first line. So usually there's something like, oh, this is the first SIGPwny stack challenge or something like that. And you just want to get rid of that in the input. So you receive it and it'll print that out. Then you can send the line. So in this case, we're sending line A times 8, which means we're sending 8 A's. Now, pwn stack 0, I know because I wrote this challenge, it's a buffer of size 4, which means you're just gonna, I'm gonna go mute that with a second we're done. Which means it's just gonna overwrite past the 4 and go into a buffer you're not supposed to be able to write into. This is ridiculous. Right now, of all time, I know what it is. I know what it is. And then after that, it's really important that you hit interactive, because if you don't do that, it's not going to show anything else. Hi, come on in. If you don't do connection.interactive, it's not going to show anything else. So it's really important that you do that. Okay. Let's go to the next slides. Oh, this is also me, but give me a second. Let's shut up Discord. So, we mentioned before that the goal was to overwrite this return address. And the return address is basically where the program goes when you are done with running a function. So it's, hey, I'm going to do something, and then when I'm done, here's where I should go. So we want to overwrite that, and here's why. The example that Chris and I came up with at 11 at night last night, which is actually, I think, really good.
That was about midnight, maybe even 1.
1? Whoa, jeez. Is doors. So, next slide. Step 1, a program begins a new function. The analogy here is that I'm walking through the door. The hallway is the previous context for where I am. In other words, it's the return address. I'm walking into the door and I'm the current location of where the program is. It's EIP. So that's the current instruction pointer. That's where I am in the function. I'm coming into this apartment, into this function. And then, step 2, I save the return address onto the stack by closing the door. I don't know what it is anymore. I just know that, okay, this return address was the hallway. It's going to be the hallway when I get back. So thumbs up, great, it's ready. After that, I go execute the function to completion. So, I'm vacuuming the floor and I'm eating some Fruit Loops. I'm doing whatever I want to do. And then when I'm done with that, I go back and I open the door again to try and go back to the hallway because I'm done in the apartment. And what's going on? That's not the hallway, that's the nether from Minecraft. Whoa. Yeah, that's the nether from Minecraft. We had Rick Astley, but it kind of didn't make sense because it's like, why would Rick Astley be on the other side of the door? That's a person, not a place. So yeah, this is also a challenge. I made a really great PNG of this for like 10, if you want to do it for like 10 points, Photoshop me into something weird. So does anyone, how that actually applies is, well, I mean, it's kind of a one-to-one mapping. When you're done with a function, it's like a person being done in a room and you just leave the door. If you overwrite the return address, when you open the door and walk out, you're going to go somewhere else. And it doesn't matter. The program has to go to that other place. So the whole goal is to make it go to where you want it to go. Here's another great example of what's going on here. So there's an innocent program entering a function, and then all of these malicious attackers come in and move over their own code right at the return address, which is the door. And when the person's done, they're somewhere completely different. So, yeah, I mean, does that kind of, is that a decent analogy? Because if so, we're probably going to use it in the future. So yeah, that's what's going on with control flow hijacking. That's what it's called. So here's the actual technical explanation for it. Do you want to cover this one, or I can do it? It's easy.
Yeah, sure, I can do it.
All right.
So up in the top left again, we have another program called vulnerable, another function called vulnerable. And we only have one variable on the stack this time, just stack bar one, and we call that vulnerable function gets again, which will take whatever the user input is, and write it into stack bar one. And then if you look at the bottom left here, our user input is 4 A's, 4 B's, and then some hex digits. So what's going on there? First off, those 4 A's will overwrite the 4 bytes that are in stack bar one. Then we have that frame pointer, which I mentioned earlier, which for now you don't need to know what that is, just know that it's 4 bytes and it's there. So that's what the 4 B's are for, to overwrite that. And then after that is the return address. So if you put those 4 bytes there at the end, they'll get stored into the return address. And in this example, we have a function called win, which based off some previous knowledge, is at that exact address. So if you store that address into the return address, when this function finishes, it will jump to that win function.
So then one more thing real quick before we keep
Yeah,
going. As you can see, we've got AAAA, which overwrites it, then BBBB, and then something weird is going on here. It's rendering, it's backwards. So that is another thing that needs to be considered. And this is why Pwn is hard, and this is why we waited so long to kind of teach it to you, because it's confusing. So what's going on here is there's something called endianness, and endianness is the order in which bytes are stored, or like numbers are stored on a computer. This is little endian, which means it's being stored from right to left. So in reality, if you want to write this address 08044232, you got to go backwards. 08, then 04, then 42, then 32. And it's by byte. It's not by like each hex value. It's weird, but just, you know, something to be aware of.
Oh.
So yeah, that's just what I explained. So here's the Pwn tools version of that. Yeah, so P32 is a Pwn tools function that'll convert the win address to the proper address. And that the proper address in this case is a little endian address. So it's not, you shouldn't have to worry about it too much, but it's just something to be aware of if you're not getting the solution right. So, all right, yeah, so that's the Pwn tool solution for a challenge like that. This is you.
All right, so in the previous example, there was a function in the program called win that we wanted to jump to. But what if there is no function in the program that we want to jump to achieve whatever our goal is? So if there is no pre-existing function in the program that we want to jump to in order to achieve our goal, it's possible to write our own with a thing called shellcode. Actually, go to the next slide and then come back to this one.
Perfect.
Okay, so an example of what, and then could you move the?
Yep. There we go.
Yeah, so an example of what shellcode is, since that's a new term, it's just a fancy word for bytes you get when you're compiling the program. And these bytes represent instructions. So technically, you write shellcode anytime you make a program and compile it. And you can write your own, which is hard and requires a lot of understanding of assembly, or you can use a database like is in the link over there. If you want to find it quickly, you could just Google that term, but it's just bytes that represent instructions that get executed.
So what is the shellcode that we want specifically is something that will open up a actual shell, like terminal. So that's what we're going for here. Yeah, just pull it back up.
Yeah, that's fine.
Okay, so we have another similar function to what we were doing last time. And last time, remember, we were overwriting the return address with the address of this win function. But what if we overwrite the return address with the address of something that's on the stack, the address of something that we can control? So in this example here, you have your 4 A's, your 4 B's, and then instead of putting the return address of an existing function, you're putting the return address of the stack itself. And then after that, you're putting the actual code. So when the program returns and it jumps to that return address, it's really only going to jump a little bit further because we're staying on the stack, and it's just going to start executing that code that's sitting on the stack.
So
And this is just a simple example of how you would do that in Pwn tools. I think the main point of this slide was just to show that when you're putting a long string of bytes in Pwn tools or Python, to keep in mind that it follows that format, and you got to make sure to have that little b there to signify bytes to Python. Okay, so in the previous example, we were putting executable code or shell code on the stack. But what if the stack is non-executable? So the entire idea of shellcode is kind of dead on modern computers. All modern computers have these things called exploit mitigations, which are in place to make sure methods like what we just talked about don't work. And the specific one that prevents shellcode is called data execution prevention, or DEP. And it marks every region of memory with 3 different flags: read, write, or execute. And then on the right here, you can see that sort of memory layout like we looked at the beginning, and then the corresponding flags that are assigned to each one. So you can see the heap and the stack have the flags RW, which means you can only read and write to them. If you were to hit a return address that jumped to the stack, and it would start trying to execute code that's on the stack, the program would the CPU would first see, oh, wait, there's no execute flag assigned to this region of memory, and it will immediately crash because it doesn't have permission to execute code in that region of memory. And yeah, it prevents buffer overflowing your own instructions onto the stack, which is what we were just talking about with shellcode. And then also the program itself, that text section, which is where the original instructions of the program are based at, does not have a write flag. So if you had some sort of arbitrary write, you wouldn't be able to just overwrite instructions on the program to start doing new things that it was never meant to do. It prevents both of those scenarios.
There's a lot more here. We're not gonna need this one, I don't think.
How much time are we at?
We're past. So,
Okay, yeah, if these are super interesting and will be in place on all modern systems. So if you ever want to take the PWN knowledge you learned here and expand it past the challenges that we have, and maybe we'll get into more on Sunday. Take a look back at these slides and check this out.
canary is important though, because there are several challenges that have the canary in them. What a canary basically is it's a callback to the old canary that they would bring down into coal mines, where if the canary died, you would know that the canaries have weaker lungs. So if they would bring the canary down, and if the canary died, they would know, okay, it's time to get out of this coal mine because there's a gas leak, or there's no air, or there's something bad in the air. So that was just a really old, kind of messed up method to figure out when something's going to go wrong. So in the purpose of exploit mitigation, a stack canary is just like a random value that is on the stack that gets checked before you return to whatever you were previously doing. And if that's been changed, you can reasonably assume that someone's trying to like attack the stack, or there's like a bug or something similar. So if the stack canary gets changed, the program will just crash. So that'll be important for, I think, stack 2. So yeah, that's it. So we've got a bunch of challenges for you. If you've done them all, please help someone else. If you haven't done all of them, try to finish them all. They're pretty approachable, and we've got lots of starter code, and we show you the source. So this is a lot about actually trying to execute an exploit versus reverse engineering that exploit and figuring out how to do it. So our next meetings, real quick, Sunday seminar is going to be PWN 2. That's going to be some of the more advanced things that are covered. It includes stuff like rectlibc and ROP, which are some pretty cool ways to get around dead execution prevention. And then GOT and PLT, which are some other thing. It's the global offset table and the procedural linkage table. So if any of these things sound interesting to you, Kevin's going to cover most of them. And then some other just advanced stuff. And then next Thursday is I'm so excited for this meeting. We are doing physical security. So that's probably about 5 minutes of how to secure your house for slides, like 5 minutes of it. And then the rest of the meeting is we're just going to pick locks. So like we have $100 worth of locks and lock picking kits and all that stuff. And we got like a fake door, and like we even have like a safe that ACM has let us try to crack into. So if anyone wants to learn how to do safe cracking and wants to crack into a safe, let's do it.
Because we don't know.
We don't know.
We don't currently know.
We don't know how to do it. ACM just hit us up and was like, "Yo, we got a safe that we need broken into."
How much time do we have?
As long as you want. We'll stay really late that day. So if you want to just keep trying to open it up, if you want to keep trying the locks, we'll stay as late as you want. So that's the meeting. I'm gonna end the share and then do the recording. Stop the share. Hello, hello, stop.